Go.
Our presentation is on the X-ray, X-ray production, and X-ray use. X-rays are relevant to energy because they are energy. X-rays are electromagnetic radiation of short wavelength produced when high-speed electrons strike a solid target. The wavelengths are so short that they're outside of the visible light spectrum. X-rays are what we use today in radiographic imaging procedures. There are also X-ray telescopes that can monitor high-energy activities in space, like a black hole swallowing a star, and there have, in the past, been attempts to militarize the X-ray. As will be explained in detail later, X-rays are produced, fired at the human body, which in turn produces a silhouette-like image on a medium behind the human body. The X-ray process was invented in 1895 by Wilhelm Conrad Röntgen, who was subsequently awarded the first ever Nobel Prize in 1901 for revolutionary observation and utilization of the X-ray. His guinea pig for the X-ray experimentation was unethically his wife, whose hand was the first ever observed X-ray produced image. The use of X-rays for medical purposes was pioneered by Major John Hall Edwards in 1908, who later had to have his left arm amputated because of the spread of X-ray radiation burns on his arm, which is a testament to the dangers of the X-ray. The X-ray's most infamous use was in shoe retail, where it was used inappropriately to regularly check a shoe's fit, which, because of repeated exposure, caused radiation cancer in customers, ultimately calling for a ban on the device. By refining the process, limiting the amount of X-ray exposure necessary to produce a medically useful image, and putting in an array of safety measures and equipment, X-ray-induced cancer in modern medical practice is very rare.
So now that we know what X-rays are and we've gotten a brief description of how they work, we really need to get into exactly how it works. So just for the essence of time, we're going to be really basic with this procedure. We're going to take kilovoltage and milliamperage and we're going to apply it to a vacuum. So here's our vacuum, which is essentially our X-ray tube. The cathode is the negative end and the anode target is the positive end. What happens when you take voltage and milliamperage and you apply it to tungsten, which is the filament here, it's going to heat up to white hot incandescence. It's in essence going to make a huge cloud of electrons which are going to be fired rapidly by the kilovoltage that you've applied to it to an anode target. The anode target is made of a substance called molybdenum, which is very, very hard. That's good. We want it to be hard because we don't want it to pit. That's bad. So when the electrons are fired at the anode target, they in essence push X-rays out in a straight line. Then once the X-rays are fired out, here's our new little schematic down here. Here's the X-ray tube. We've got these X-rays being fired out in a straight line to a receptor. In between the receptor and the source is our person. So when you need an X-ray, what's happening is high voltage electrons are being actually fired through your body. Now your body's made up of many different substances. You've got your soft tissue and you've got your hard bone. So what happens when the electrons are pushed through your body? They're going to go easier through the soft tissue, of course. And it's going to be harder for it to pass through the bone. So what happens after the X-rays are fired through? The receptor picks up the extra electrons. This receptor here is made of very expensive and very rare phosphors that fluoresce when electrons hit them. So here's our little man. He's going to get a chest X-ray. We're firing X-rays through him. In his chest, there is variations of bone and soft tissue. During this time, the electrons have passed through and they've created a reaction inside of the phosphor that's going to show us exactly how many electrons have passed through. A lot of electrons are going to pass through his soft tissue, but not so many are going to pass through the bone. So here we've got the receptor. After we take that receptor that's been affected by the electrons, the phosphors create a latent image, which is just a reaction that stays on the film for a few minutes. We drop it into a processor and the computer computes an algorithm which in turn makes an image on our screen to view it. And that is in essence how it works. So now we've talked about our receptor. I've told you that we drop the receptor into a digital film processor so that we can actually see the image that we shot. So as I said before, our little man here got a chest x-ray. So here is a real quick schematic of what a chest x-ray will come out like. Here we've got the chest x-ray, and you'll notice where I marked in black, that's going to be where very few electrons got through to affect that phosphor. But anywhere that is white will show that quite a bit of electrons have passed through. All the properties of x-rays that we're going to get to next are going to explain why, in fact, some of our image is black and some of it is white. So I'm going to bring you over here to the properties of X-ray. X-rays are very high energy, which means they have a short wavelength. Along the electromagnetic spectrum, wavelengths that are longer are very low energy. X-rays are very high energy. We want them to pass straight through the body. So they are very short wavelength, which brings us to our second property of X-ray, which is they're highly penetrating. That's pretty self-explanatory. We wouldn't want an x-ray that didn't penetrate. The whole point of an x-ray is to penetrate your body's tissues in order to see inside the body. Also, going along with this, it's heat producing. X-rays are ionizing radiation, which means that when you have an atom and you take very high energy, it's going to knock an electron out of orbit. When that happens, that creates a very small and negligible amount of heat. Also, along with the free electrons, can cause biological harm. When we have free electrons floating around in our body, they are able to cause harm to our other tissues. That we can get into later on. There are many effects of radiation on the human body, and we need to have in place certain measures to make sure that patients and radiation workers especially are not negatively affected by this. So we talked about before that x-rays can cause biological harm. So that poses the natural question, how do we protect ourselves as workers and as patients from this harm? Radiation protection. When we talk about radiation, we talk about the risk versus the benefit. When you are sick or hurt, obviously you are going to need to be treated. So we can't do that sometimes without imaging. We need to make sure that the amount of radiation that we use isn't so high that it's harmful to your body, but it's high enough to create a quality image so that we don't have to repeat it. Repeating x-rays is not good. We want to get a good image the first time, every time. So we live by the acronym ALERA, or as low as reasonably achievable. That's what we want to keep the radiation dose at. We want to use the smallest amount of radiation on your body to make a great picture so that we don't have to take it again. So here's our little human body over here. As I talked about before, it can cause biological harm. The most damage can be done to our rapidly regenerating cells. These cells live in several places in our bodies. The first place they live is in our gastrointestinal system. So our stomach, the lining of our esophagus, and the lining of our colon. These cells rapidly regenerate. They're always growing. They're always moving around. So we want to protect them. Also down here, we've got your reproductive organs. And if you've ever had an x-ray before, you've noticed that somebody's probably come along and strapped a nice, heavy apron over your chest. That's to protect your reproductive organs. Now the second place that these rapidly regenerating cells live is in our blood. We want to protect all of our bodies, so what we do when we can't cover up our blood, obviously it's in our entire body, we restrict the area that the x-ray beam is going to, hence limiting the radiation that's going to the body. So as I talked about before, radiation affects our rapidly regenerating cells. We've got germ cells, which in women are ovaries, men it's the testes, it's our reproductive organs. Then we've got our blood and the gastrointestinal organs in that order. We've got bones and nerve cells over here, which fortunately for us aren't that radiosensitive, meaning radiation doesn't as readily affect. Hi Sydney, my name's Sarah and I'm going to take your chest x-ray today.
Okay.
What's your last name?
Morin.
And can you spell that for me?
M-O-R-I-N.
And your date of birth?
6/20/94.
Okay, so we're going to do a chest x-ray. It looks like you've had a cough.
Yes.
How long have you been coughing?
About 2 weeks.
All right, so we're going to get a chest x-ray. We're actually going to take 2 pictures of your chest.
Okay.
Is there any chance at all that you could be pregnant?
No.
No. Okay, very good. Okay, I'm going to have you come right up to my board with your chest. There you go, just like this. Stay just like that. This board's going to move down. Good. My hand's going to go right down the back of your spine. I'm going to have you roll your shoulders forward and then take your arms and put them around the bottom of the box and give it the most awkward hug. There you go. Sydney, I'm going to put this shield behind your back. It's just to protect you.
Okay.
Okay. Well, I take the x-ray. I'm going to have you take a big breath in. Go ahead and take one big breath right now. Blow it all the way out. Good. Take one more big breath in and hold it. Okay, you can breathe and relax away from my board. Good. All right, we have one more picture to take, and that's a side view. I'm just going to process this.